Welcome back. Today we're going to look at a particular optimal control problem that's foundational in the theory of economic growth, and it's called the Ramsey or Cass-Koopmans model. This is something that was first developed a long time ago by Ramsey, but then independently Cass and Koopmans came up with similar problems later on. And ultimately what we're doing is taking the very basic solo growth model, which you probably saw as an undergrad, or maybe in a master's degree, and they endogenize the investment rate. The solo growth model investment is some given constant, but in modern macro we want any statistic such as the savings rate to be the result of agent behavior. Any macro statistic should have a microeconomic foundation, and that's what we're going to get with this model. Let's have a look. So to analyze the Ramsey-Cass-Koopmans model, it's important to first of all realize what we're doing here. What we're going to do is we're going to solve the planner's problem that I'm going to describe. There is, by analogy to what we did in discrete time, a continuous time version of this with markets, which is going to have the same allocations and dynamic solution as the planner's problem because there are no externalities and no other sources of market failure here. So in this economy, we're going to have aggregate outputs, which will be called Y of t. And here we're using capital letters to refer to aggregates. So this output has two uses. One of them is consumption, and the other is investment. And we're also going to have a production function. So y is going to equal some function which uses two inputs but has three arguments. One is capital, and the other is labor. The third variable we're going to have here is a productivity term, which enters the production function multiplicatively. So growth in productivity is labor augmenting. Next, we have a law of motion for capital, which is capital changes, and it changes due to two flows. One is a flow into the capital stock, which is just aggregate investment. The other is a flow out of the capital stock, which is depreciation. And depreciation occurs at a constant rate. So the flow of depreciation is delta times K. Now put these two together, and we're going to get budget constraint, which is simply this, replacing that by F. Now, let's try and get this all in effective units of labor. So let's take this and divide it by A times L. So A times L, we're going to refer to as effective units of labor. Shorthand. Next, we're going to do two things. One is we're going to define CT as consumption over effective units of labor. Similarly, Similarly, IT is going to be investment per effective unit of labor, and little k t is going to be equal to capital by effective units of labor. Second, we're going to assume the production function f displays constant returns to scale, or another way to put it is that it's homogeneous degree 1. So then what happens? Well, this is just small c. This is just small I. And this becomes f of small k times 1 and 1. So as a shorthand, let's now define little f of k to equal big F of k and 1. And so we can write this in a simpler form just as f of k of t. Great. Next, we're going to assume that things here grow at constant rates. So population grows at a rate n. In addition, A, productivity, grows at a rate g. This means two things. It means that L dot over L, that's a growth rate, equals some constant n, and it means that A dot over A equals some constant g. This is the same thing as saying that L is some L0 times e to the nt. And similarly, this is the same as saying that A is some A0 times e to the gt. The next thing we would like to do is find an expression for small k dots. Now, the next thing we would like to do is to find an expression for lowercase k dots. And if we can do that, then we'll have been able to transform everything into lowercase variables. How are we going to do that? Now observe that k dot is just the derivative of k over al with respect to time. That's by definition. So let's just compute that using the quotient rule. First, we get the derivative of the first one, the derivative of the numerator, which is k dot, times what's in the denominator, minus the derivative of the denominator, which is going to be a dot l plus al dot times the numerator, k, all divided by the denominator squared, aall. Not the most conventional notation, but it'll be convenient. Now let's write this down here. Separate this from the rest. And you can see that one of the ALs is going to cancel out. Great. Now, observe I can multiply the top and bottom of this by k. And I'm going to factor out k from this whole thing. Notice I can also factor out AL. So now this one just becomes k dot over k. And this becomes this, and the k disappears because I factored it out. Finally, one more simplification. Let's split up these into two fractions, like so. Here you have an L canceling, and here you have an A canceling. And so we have a fairly straightforward expression where I've suppressed the time argument. K dot is just this. So let's write that down. Now let's simplify. This is just K. This is the growth rate of capital. This is our parameter G. And this is our parameter N. Now we can write this in the form of a growth rate. And we have that the growth rate of this adjusted capital in terms of effective labor is the growth rate of the aggregate capital minus the growth rate of productivity minus the growth rate of the population. Now let's go back to our aggregate equations where we have this function, which is the resource constraint, and let's add into it the capital accumulation function, which tells us that investment is k dot minus delta. Investment is k dot plus delta k, so let's replace that here. And of course, because of local non-satiation, this becomes an equal sign. No resources will be wasted because utility is strictly increasing. We'll look at the utility function in a second. We can rearrange this so that it's in terms of k dot. So this goes over here. This goes over here. Let's switch sides. And we're done. Now, multiply and divide both sides by AL. So AL over AL, I'm suppressing T. AL over AL. That means that this is going to transform here into f of k, small f of k, AL over AL here. This, of course, becomes small c of t. This becomes small k. Now divide both sides by k. We have this. Now we take this equation here and plug this in. Notice that this is just 1 over small k. So if we multiply both sides by small k, this will cancel, this will cancel, and now we'll have k multiplying minus g and minus n. And so now we have a law of motion for k dot. To sum up, k dot equals f of k minus consumption minus the sum of delta g and n times k. So from the production side, we have a differential equation characterizing how capital changes. What's missing, now that we've solved for technology, is the preferences. So now preferences. What are the agents going to maximize? The utility function of these agents is going to be this. The integral from 0 to infinity of some function u of c with discounting. Now we're going to have discounting by some rate rho, exponential discounting. So this is an autonomous problem. However, remember, we also have population growth, and the way we're going to have that work is the same way we did before. We're going to say that each household has a number of agents that grow slowly over time, and they care about the utility of the agents in the entire household. And so we also have, therefore, the weight here going up over time at rate n. So we can just put these two together and write it more succinctly this way. Now, finally, let's solve this as an optimal control problem. What do we need to do? All we need to do is write down the Hamiltonian. So to apply optimal control problems, we need to figure out what's the objective function. That's this, no problem. And then we have to figure out what is the state variable. It's k dot. And finally, we have to figure out what is the transition function. It's this. So we have everything we need. Now we can write this down as a present value Hamiltonian or a current value Hamiltonian. I'm going to do this in the current value Hamiltonian way, given that this is an autonomous control problem. So the first thing we need to do is to write down the objective function, which in the current value Hamiltonian setting is just this. That's the integrand. Then we have a multiplier times the expression for k dot, since k is our state variable, and that's this. That's our Hamiltonian. The control variable is c, the state variable is k, and mu is our multiplier or co-state. What's the optimality condition? The optimality condition, remember, is that the derivative of the Hamiltonian with respect to the control variable must equal 0. And what does that mean? Here is the Hamiltonian. The derivative of this with respect to c is just u prime. The derivative of this with respect to c is -1. So we get that this minus the multiplier equals 0. Next, we want to write down our co-state equation. And the way we're going to get that is by showing that the derivative of our Hamiltonian with respect to the state variable, which is capital, should be equal to mu times the discount rate. The discount rate is rho, but remember we also have population. So actually discount rate is not rho, it's rho minus n minus mu dot. So now let's evaluate that derivative. Capital doesn't show up here. Here we get f prime, here we get 0, and here we get these constants. Finally, our state equation is just this. So what are we going to do with this? Note that from the optimality condition, we have an additional way of finding out what is mu dot. We have mu dot here, but we can also get mu dot here by simply deriving this expression with respect to time, taking the total derivative with respect to time. Here we would get u double prime times c dot. And here we just get mu dot. We can plug this into the co-state equation and replace mu dot. And notice we can also replace mu because we know from the optimality condition it equals to this. So we've eliminated multiplier mu, the co-state mu, entirely from our equation. Now let's put this in a slightly more useful form by dividing both sides by u prime. So we divide both sides by u prime. This cancels to become 1. This cancels to become 1. And notice that this n cancels with this n, rather than minus n. And you subtract rho from both sides. We have this expression. Finally, divide both sides by this. We're going to get that c dot equals the reciprocal of this times all of this. So the solution to this problem is characterized by a pair of differential equations. This one, which is the state equation, which tells us how capital evolves as a function of consumption, and this one, which tells us how consumption evolves along with capital. Now, remembering that k at date 0 is given, in principle, this tells us, together with this, how this economy is going to evolve. Finally, so far we've been working with a general utility function here, but in practice, as we've discussed, we'll very often be using a particular form of u, which has constant relative risk aversion, and that is the following function. Now you may wonder, what is this -1 doing here? What happens is that if you take the limit of this function as sigma goes to 1, it actually turns into the natural logarithm of c. You can show that with L'Hopital's rule, but it's not going to work if this -1 is not there, even though it doesn't actually affect behavior for any particular value of sigma. Now in this case, this expression here is going to have a particular value. Let's figure out what it is. Well, first, let's take u prime. U prime of c, of course, is just one minus sigma times this. So 1 minus sigma cancels out, and we're left with this simple expression. What about the second derivative? The second derivative of u with respect to c, here we multiply by minus sigma and divide by c. So this whole expression equals minus this divided by this. Let's cancel our minus signs, and you can see that this cancels here, and so what we're left with is just this. And so for this particular utility function, our function here is going to have a very interesting and useful form. Divide both sides by c, and you'll observe that now we have an expression for the growth rate of consumption in this economy as a function of capital. Again, that together with our state equation gives us two differential equations that are going to characterize the behavior of this model. Finally, I'd just like to say that I knew Dave Cass. He was one of my professors in graduate school, although he didn't teach many classes. He was very influential in how well he treated the graduate student body. He set up a lounge for us. He was always available to talk about anything, whether about economics or indeed anything else. We would often go to his house. And so this video is dedicated to David Cass.